Okay, so welcome everybody again. So just as a quick reminder, I wrote down some of the key equations from last lecture yesterday. Uh, just as a reminder, we were talking about the search for the isotropic stochastic background. And this is the estimator that we're starting with. So we take the time series of the two detectors, multiply them together, and multiply with some filter, and then integrate over time. And we found that when we convert everything into frequency domain and do the plane wave expansion of the gravitational wave signal, we find that the expected value of this estimator looks like this. So there is this term omega GW. So the expected value is closely related to the actual energy density in gravitational waves, which is what we want. There is this factor, the overlap reduction function of gamma 1, 2. And you may remember that the form for it, but it involves the phase delay between the two detectors. And that's because the two detectors are in general located in different geographic locations, so they're physically separated. And it also includes the actual response of the detectors to the gravitational waves, because in general the two detectors will be oriented differently, pointing in different directions on the sky. So those antenna pattern effects are incorporated inside of this gamma function. And these are purely geometrical effects, so they have nothing to do with the data itself. So they can be evaluated once before the analysis is done, and they apply to that specific detector pair that we're using. There is an F cube term in the denominator, which we talked about before, emphasizes the low frequency contributions and gives us more sensitivity at low frequencies. And then there's the optimal filter Q, which we found by optimizing the signal to noise ratio. The variance corresponding to this estimator Y looks like this. So you can see that it has the power spectral densities of the two detectors, and again the filter. And the filter itself takes this form. So it depends on the actual energy density spectrum in gravitational waves that we're searching for. So this is, as we said, an assumption that we make when we do the analysis. We choose what kind of a spectrum we want to look for, and then calculate the optimal filter corresponding to that choice. So it depends on the energy density that we're looking for. It depends on the detector network that we're using, specifically the detector pair that we're using through this overlap reduction function. And it depends on their power spectral densities. And then the SNR takes this form, and you see several things from this equation. First, our SNR grows with the square root of time. So the longer you observe, the better your signal to noise ratio will be, although the improvements will be diminishing over time. Again, the SNR depends on the overlap reduction function on the assumed spectral shape that we're looking for, and it suppresses the frequencies where the noise is very large, where P1 or P2 are high, which includes both, for example, the low frequencies where the seismic noise dominates, very high frequencies where we're losing due to the laser shot noise, as well as various narrow frequency bins where, for example, we may have the 60 hertz pickup. This is the power mains, or the various calibration lines that are used to track the performance of the detectors over time, and so on. So this is, in the end, this choice of the optimum filter allows us to pick out the frequency bins that are the most sensitive and weigh them more than others. So that's more or less how far we got last time. There are a few things that we can say now, or to take this a little bit further. The spectrum omega GW that we end up using in practice very often we would choose a simple power law. So we would write omega GW of f to be some amplitude times frequency divided by some reference frequency to the power alpha. And this reference frequency it is a completely arbitrary choice, but we typically choose it to be in our band. So 25 hertz would be a common choice. And the values of alpha that we typically choose are 0, 2/3, and 3. Why these? Well, alpha of 0 means that we're looking at the flat spectrum, flat energy spectrum in gravitational waves, and many cosmology models will look flat or nearly flat in the LIGO frequency band. So that's that choice. 2/3, as we saw a couple of days ago, is the f to the power 2/3 is the spectrum of the compact binary stochastic background models. So this is one of the most interesting models for us today because it's the most likely one that we will see. So hence we choose that particular value. And 3, the value of alpha equals to 3 is motivated by the fact that some of the astrophysical models, like the magnetar models or the supernovae, tend to have a relatively high value of alpha. They sharply increase with frequency. And so this alpha of 3 is supposed to kind of capture those kind of models or to be representative of those. It is also the case that when you choose alpha of 3, when omega goes as frequency to the power 3, the power spectrum h of f will be flat because remember that f cubed term that relates omega and h. So omega goes as f cubed times h of f. So if you choose omega of f to go as f cubed, then h of f, which is a strained power spectrum, will be flat. So those are the choices we make. And as we also discussed yesterday, you can do this analysis in multiple ways. It tends to be the case that for us, the most sensitive frequency band is between 20 hertz and maybe 100 hertz or so, depending on the choice of alpha. So you can do the analysis in that entire frequency band. And that's fine. The analysis will we can choose the value of this lambda here so that the expected value of y will be exactly equal to omega alpha, so that the result of the analysis is an estimate of omega alpha. So that's certainly a possibility, and that's one of the results that we typically quote in our papers. But you can do also the analysis, as we said yesterday, in small frequency bins. So in what I mean by small bins, typically we would take this frequency band from 20 to, let's say, 100 hertz, and then we split it into, let's say, quarter hertz bins. Or sometimes we use 1/32 hertz bins, or sometimes we use 1 hertz bins. The idea being that you can repeat the analysis above in each small frequency bin, and in each bin you can assume the frequency to be you can assume omega to be frequency independent, so alpha of 0, and that allows us to basically estimate the energy density in gravitational waves in each bin independently. So as a result, we will have the estimator y sub I and its corresponding uncertainty sigma sub I for each frequency bin I. Okay, so now instead of having one measurement of omega alpha, we may have 100 measurements of omega alpha, one for each small frequency bin. And the reason this is interesting is because you can now start to, you can basically pretend that you have measured the energy density along many frequency bins, and you can now compare that to various theoretical models. And the way you do that statistically, in a statistically rigorous way, is by defining a likelihood. So the likelihood function in our case will be exponential. Sorry, it will be Gaussian. So what we're writing down is the likelihood of observing the set of yi's and sigma i's given some set of model parameters. Okay, and this function will be, as I said, Gaussian, so it will look like an exponential. And inside of the exponent, we will have minus yi minus omega m. So just bear with me, I'll explain what I mean by all of this. So this gets squared divided by 2 sigma I squared, and then we take the product over all I. Okay, so what does this mean? Well, in this likelihood, in the exponent, what we're comparing is the observed value of the energy density in the bin I, in the frequency bin I, with the prediction of some model. So omega m here is a model of the stochastic gravitational wave background evaluated at the same frequency bin Fi. And this model is depends on some parameters theta. Okay, so in the case of the compact binary stochastic background model, the theta, for example, would include the chirp masses or the parameters that describe the chirp mass distribution. It will depend on the maybe parameters that define the time delay distribution, perhaps the parameters that describe the star formation rate, and so on. So all of those would enter here. Some of the parameters we can choose that, or we can decide if we think we know them well, we can fix them. Others can remain free, and so on. And then we of course divide by the sigma squared corresponding to that to the measurement in that particular frequency bin. So we can write this down for each frequency bin, and since the frequency bins are effectively uncorrelated and independent, the overall likelihood for the entire measurement then across all the frequency bins would be the product of the likelihood functions in each bin. So this would be the likelihood function, and of course, if we choose the parameters theta such that the prediction omega m is close to yi's, right, then the numerator here will be relatively small, and therefore the whole likelihood function would be relatively large because we are raising exponential to the negative small number. However, if we choose parameters theta such that the omega is very different from y, so we have a bad fit, then this numerator here will be relatively large. You square that and put a negative sign in front and then exponentiate, you will get a very small value for the likelihood. So by maximizing the likelihood, by varying the parameters theta that maximize the likelihood, we find the best fit to our data. And so this is the process of likelihood maximization is kind of a standard situation in many areas of physics or astrophysics. This is a way of estimating parameters. Now you can also push this into the Bayesian statistics. So we can use the Bayes theorem, which basically allows us to write something like this down. So let me write it down and we can talk about it. So this is the posterior distribution which is a distribution of the parameters theta given the data yi and sigma I given our measurements. That's equal to the likelihood of observing yi and sigma I given the theta parameters times some prior distribution of the parameters theta divided by some general distribution of observing yi and sigma I data. So this is just an application of the Bayes theorem. You can think of these as conditional probabilities, both the likelihood and the posterior distribution. And what we're saying here is that the likelihood here describes our measurement. It describes, or rather it describes the information we get from our measurement. If we combine that with some prior knowledge on theta, so for example, this could include the fact that masses have to be positive, or maybe we have constraints on some parameters from outside experiments, we can put those constraints inside of our prior distribution and multiply that with the likelihood, and that gives us the posterior distribution of the parameters theta, which then allows us, so this posterior distribution is a distribution of the values of the parameters that we are after. So we can look at, for example, we can constrain directly the parameters using this posterior distribution. So we can ask for 95% confidence intervals for a particular parameter and so on. So this is the statistical way of interpreting the results of the isotropic search. So once again, to kind of show the big picture, once we repeat the analysis in each of the small frequency bins, and we get the estimates of our cross correlation estimator y in each frequency bin and the corresponding errors, we can define this likelihood function, which is basically a simple Gaussian distribution. And when we multiply with some pressure on a given model that we're studying, that allows us to compute the posterior distribution on the parameters of the model. And this posterior distribution can then be used to produce our final results, meaning constraints on a particular parameter or sets of parameters within the model. So at this point, I can maybe switch to my slides and maybe show you some recent results. Okay, so let's see, this would be the screen. So you should be able to see my my slides at this point. Okay, just
we
to
can
confirm.
see your slides, yeah.
Excellent. So this is the slide saying detection strategy. So this is basically a summary of what we have done. Again, this is the cross-correlation estimator in time domain. This is what it would look like in the frequency domain. The theoretical variance corresponding to this estimator, so that's our sigma. The filter that we talked about, a typical template that we use for calculating the filter is a power law. We can choose the normalization, or here I called it N. On the scratch pad I used lambda. But anyway, you can choose this N such that the expected value of the estimator Y is equal to omega alpha or proportional to it. So that's basically what we discussed. This plot here shows the overlap reduction function. This is the gamma function. I guess there are a couple of choices here. H1, H2 were all detectors that were co-located, and for them the gamma function would be 1. H2 was H1 is of course the Hanford detector. H2 existed in the initial LIGO era, and it was co-located with H1. So that's why the overlap is 1. But for H1 and L1, so these are the two LIGO detectors at Hanford, Washington State, and Livingston, Louisiana. So they're separated by about 1,000 kilometers. You see that the overlap reduction function is non-trivial, right? It starts off relatively close to 1, but already at 60 hertz we have our first 0, and that the 60 hertz is basically the combination of the distance between the two detectors, Hanford and Livingston, and the speed of light, which is the propagation speed of gravitational waves. And that repeats to 120, 180, and so on. So we have zeros in this overlap reduction function, meaning that at certain frequencies we have no sensitivity to gravitational waves. And you also see that in addition to this F cube term that we talked about, and the fact that we lose sensitivity at high frequencies simply because of the shot noise of the laser in the gravitational wave detectors. On top of all of that, you see that even the overlap reduction function suppresses the high frequencies. So it favors the frequencies below 60 hertz or so. So in the end, when you put all of that together, we lose very quickly the sensitivity at high frequencies, and this is really what we end up using. This region here below 60-ish hertz tends to be the most interesting for the stochastic searches. Okay, so for O3,
can I ask a simple
yeah.
question? So how do we understand this overlap reduction function going to zero? Is it because, for example, sine waves of those frequencies would sort of cancel out because of different directions?
Yep, that's exactly it. When you take under the assumption that the stochastic background is isotropic, meaning that all directions, waves from all directions have same or similar amplitudes. At that particular frequency, when you do the integral over the full sky, you will get a complete cancellation of waves coming from different directions. So that's exactly it. Okay, so some technicalities here. So when we do our analysis, we start off with a time series that are sampled at about 16 kilohertz. We downsample it first to 4,000 hertz, such that the Nyquist frequency is about 2 kilohertz, which means that we cannot see, probe or study anything beyond 2 kilohertz, and that's just fine for most of our models that we're interested in. Then we high-pass filter the data, and the reason for that is the low frequency part of the data is by far louder than the frequencies that we're interested in, starting at 20 hertz and above. So if you remember the strain sensitivity curve of LIGO or Virgo detectors, it has a very sharply increasing noise floor at about 10 hertz or so due to the seismic noise and other things. And so when you do analysis of finite data samples, those such a large gradient, such a large range going from low frequencies to high frequencies can wreak havoc in your Fourier transforms and so on. So we to avoid that, we filter the data so as to remove the low frequency content, things below 10 hertz or so, and we use a very sharp filter, this 16th order Butterworth filter with an E frequency of 11 hertz. So that's to remove the low frequency stuff. Then we divided data into shorter time segments. In O3, we used the segments of duration 192 seconds. And sometimes we use exactly 60 seconds and so on. Each of these segments is then windowed. So the idea being that if the data starts off relatively high or relatively low, away from zero, when you do a Fourier transform of that segment, you may get ringing. So to avoid that, we apply a window that basically zeroes the beginning and the ending part of the time segment, and then do the analysis of this windowed data set, or segment, which is better behaved when you do Fourier transforms and so on. Now, when you do a window like that, you're also losing information. So what we do is we apply the hand window, which effectively removes half of our data. But then we overlap these 192 second segments. We overlap them by 50%. So that way we recover the loss of information. So once we downsample and filter the data and then window it and so on, we are ready to do the Fourier transforms for each of these segments, and then we coarse grain them to 1/32 hertz. So that's the resolution at which we study the results. So once we have all of that, we probably spend the most time on. We study the data quality of our results. Oftentimes, or usually, I would say, we define these data quality cuts before we actually do the final analysis with zero lag between Hanford and Livingston data. So when we study the data quality, we would typically impose something like 1 second time delay between Hanford and Livingston, just so to make sure that we're not biased by the actual gravitational wave background that may be present in the data. So when we impose a 1 second time shift between Hanford and Livingston, and then do the cross correlation, we expect to have zero, basically, cross correlation between the two detectors. And then we study the data both in time and in frequency domain. And in the time domain, we look at the power fluctuations in the data. So we basically look at the variance, sigma y, and we look at how it changes from segment to segment. And we impose a requirement that the power fluctuations must be smaller than 20%. Fluctuations that are larger than 20%, in our experience at least, are indicative of some sort of a glitch, some transient noise that elevates the power in data locally at some particular time, and then it's gone in the next segment. So this allows us to kind of identify these very loud glitches that may impact our data. And of course, you know that one of our underlying assumptions is that the background is stationary. This is a way of imposing the stationarity in our data. So when we impose this cut, we typically lose 4 to 5% of the data due to the non-stationarity. In frequency domain, so here you can see a typical strain spectrum. For this one was for Livingston, and it's back in 2017, so pre-03 data. You see that you of course see the main curve here, which is what we really are interested in. But on top of that curve, there is a number of narrow, sharp lines, and some of them are 60 hertz, so and the 60 hertz harmonic. So this is the power mains in the United States. But others include calibration lines. As I mentioned, those are used by the commissioners to track the performance of the detectors over time. There are violin modes that are associated with the suspension wires that hold the mirrors. There are very often 1 hertz harmonics or even quarter hertz harmonics occasionally that often have to do with things like clocks that are synchronized even between the two sites, between Livingston and Hanford, through the GPS system. So there's a number of these things that we just simply don't care for. So we, in frequency domain, notch out a number of these frequencies. We basically identify all of them. We check, especially for those that are maybe unusual, that don't fit these descriptions here. There could be occasionally lines that are couplings, maybe locally at Livingston. There may be a pump going on at relatively nearby that causes a elevated noise at a particular frequency bin. So things like that we identify and notch out so as not to contaminate our final results. And roughly speaking, we lose about 10% of the frequency band once we impose the cuts on both detectors. So in 03, we had a particular challenge which had to do with glitches. It turned out that in 03, there was a very high frequency of these loud glitches. They were sharp, broadband, and very numerous. So we could identify them with our stationarity cut, comparing the power in each segment and so on. But that ended up removing almost 50% of the data, so a non-trivial hit in our sensitivity. So to avoid that, we applied a procedure where we identify these glitches and replace them with replace the data with zeros during the glitch time, so as to effectively remove it. and then perform the stochastic analysis on this cleaned up data. And this is these two plots are basically meant to illustrate how our data behaves better after the removal of the glitches. And you can see what we're showing you is the coherence, which is effectively the cross correlation between Hanford and Livingston. And you see that it's basically it's very rugged. There's a lot of structure in it, indicating basically the impact of these very loud glitches. And when we remove them, the coherence tends to behave much better. It's basically flat, which is what you would expect for non-correlated Gaussian data. Another thing that we worry about is, so we have removed a lot of these both time transients, so glitches and so on, and frequency lines that are present in the data. But there could also be other underlying structure in the data that may even be correlated between different detectors. And the leading cause of concern, if you like, is the magnetic noise, the global magnetic noise on Earth. And you may know, you may have heard of the Schumann resonances. These are basically the standing waves in the magnetic field around the Earth that basically are effectively caught in a resonant cavity between the surface of the Earth and the ionosphere. So storms, which of course there are many of them around the Earth at any given time, thunderstorms and so on, create standing waves in this resonant cavity, and because they're standing, they are correlated between different geographic locations on the surface of the Earth. So this is to say that the magnetic field in general is correlated between two different locations on the Earth. And if this field is coupling to your gravitational wave detectors, then you have a problem because you have a correlated noise, magnetic noise entering both detectors, even though they're geographically separated. So this is something that we worry about, and we have identified two approaches to dealing with this problem. One of them is to first measure the magnetic coupling. So what we do is at various places around the LIGO and Virgo detectors around these detectors near the corner stations and sometimes at the end stations as well, we create, using coils, we create strong magnetic fields, and we look at how strong those signals are in the strain. So how much this magnetic field couples to the strain channels of the gravitational wave detectors. And once you have so that gives us some indication of what is the transfer function between the magnetic field and the strain channels in our detectors. You need another piece of information, which is you need to know the correlation between the magnetic fields at the two sites. So you measure the magnetic field using very sensitive magnetometers at both, let's say, Hanford and Livingston. And that allows you to calculate the correlation between the two sites. And then you can combine the magnetic correlations with the coupling of the magnetic field to the strain channel at each detector to estimate the contribution of these magnetic correlations to omega GW. That's one way to approach this. You measure the magnetic correlations, you measure how much they couple at each site, and then you pull all of that together to estimate the contribution to omega. The second approach is to not necessarily estimate the contribution directly from first principles, but fit it from the data. So you create a model of magnetic contamination, and then you estimate this model along with some stochastic background model in this Bayesian scheme that I talked about earlier. So you try to fit this magnetic noise contamination, pretending that it behaves as one of the stochastic background models. So you fit for both the noise and for the signal, if you like, simultaneously in this Bayesian parameter estimation. So this is the latest result. This comes from 03. Several curves here are shown. The black solid curve at the very top is the sigma of f. So this is our calculation of the experimental uncertainty on the estimator y as a function of frequency, and it's actually shown at the 2 sigma level. And that's to be compared with the dashed black curve here, which is our estimate of the magnetic field contribution to omega. So this is this first approach where we measure the magnetic correlations between the two sites. We measure the coupling of magnetic field to a strain channel at each detector, and then pull them together to estimate their contribution to omega. So that's what this band is, and the dashed line here is the top of the band. And you see that we're basically everywhere across the frequency band. Our estimate of the magnetic noise contamination is below the sensitivity of our detector. So we're still good. It's just not a problem. But you can imagine that if we lower or improve our sensitivity, let's say by 2 orders of magnitude, we will start to actually see the effect of the magnetic correlations. The other curves here are this red curve is the PI curve, the power law integrated curve. So rather than, so effectively, this is another way of looking at the sensitivity. You take basically this curve, which shows the sensitivity at each frequency bin, and then you combine the sensitivity across all frequencies for a particular power law. And then you repeat that for all values of alpha, the power index. And that gives us this this curve, and that's to be compared with basically this band here. And again, the message is that we're at least a couple orders of magnitude above the point where the magnetic field might interfere. Okay, so this is our results combining 03 and 02 and 01 data so far. And what you see here is basically as our estimator of y of f is shown in blue, and the black is a corresponding sigma of f. You can do statistical tests of this data and show that everything is behaving as you would expect, that the ratio of y of f divided by sigma of f is a Gaussian distribution with zero mean and unit variance. There are a variety of such tests that we do. So no detection has been made. We're still not observing the stochastic background, and then we compute the upper limits on omega alpha for different values of alpha, and those are shown in the table here. The left part of the table is assuming a uniform prior in omega alpha. The one on the right is assuming a uniform in the log of omega. And you see the upper limits are at the level of 10 to the minus 8, or even better if you assume the log uniform prior. So the uniform prior would tend to be a bit more conservative and gives a little bit higher values of the upper limit. The log uniform prior we're using it because it is more sensitive to weaker signals. So we're more likely to pick out the weaker signals using this kind of prior. So this analysis here is done. Basically, you choose the value of alpha, and you have only one parameter to estimate, which is omega alpha in that analysis. In this case, you can repeat the analysis taking both omega, the amplitude, and alpha to be free parameters. So now you have a two-dimensional parameter space, and you can calculate the likelihood function that I wrote down earlier. And you can find the region in this data. So you can see that the 95 and the 68% confidence level contours of the posterior distribution in this parameter space. And so again, you see that we are ruling out high values of omega for any value of alpha, and that we're basically preferring alpha closer to 0 because, and that also comes from the prior distribution on alpha that we assume. So again, the upper limits are, as you can see, in the 10 to the minus 8 range. Okay, so this is maybe a good place to stop for a second, see if there are any questions. Don't see the chat window, so
in the chat. So if anybody has any question, you can ask up.
Okay, well, if there are no questions, we'll continue. So we have developed so far the formalism to search for the isotropic background, and remember that we assume this background to be, well, first isotropic, of course, but also unpolarized. So what we will do next is we will relax these assumptions and see how the search formalism changes. So the first thing that we will do is we will now look at the situation where the background is polarized. So the place where this enters is in the 2-point correlation function. So remember, we had we made an assumption about HA of F and omega multiplied with HA prime of
Vuc, are you presenting your slides? Because we are just seeing
I'm sorry.
the picture.
I didn't switch the share. My apologies. One sec. Okay, you should be able to see my scratch pad now, right?
Yes.
Okay, thanks for for alerting me. So I was just writing down. You remember that a starting point when we developed the formalism was in making an assumption about the 2-point correlation. So if I have a wave at frequency f and traveling in direction omega with some polarization A, where A could be plus or across, the product of that wave or amplitude of that wave with amplitude of another wave at frequency f prime, direction omega prime, polarization A prime, was given by delta AA prime, delta of f minus f prime, the two-dimensional delta function between omega hat and omega hat prime, which is written in terms of the spherical coordinates theta and phi. And then at the end, we had h of f. That was the assumption for isotropic and unpolarized background. Now we can extend this or modify this assumption. I should put a star on one of these. We can modify this assumption for a polarized background. So I will write it down. So instead of, we now have to specify right or left polarization. So f prime and omega prime. Okay, so now we will still have the delta function in frequency and the delta function in omega. And we'll divide it by 4 pi in this case. But then instead of h, we will write the result in this particular way. So bear with me for a moment. Okay, so if we have both amplitudes being the right polarized wave, then we will have the result here will be I of f plus V of f. If we have both of these amplitudes being left polarized waves, then on the right hand side we will have I of f minus V of f. So the idea being that if we have if we have two right polarized waves, the strain power will be higher than if we have two left polarized waves, assuming that V is positive, of course. And then if we have H R with H L, this 2-point correlation would be 0. So the 2-point correlation between the right and the left waves will vanish, But if we have two right polarized waves, the strain power will be different than if we have two left polarized waves. So I should also, just to be explicit, write down what I mean by HR and HL. So HL can be written as the left polarized wave would be H plus I H cross divided by square root 2, and HR is then with a minus sign. Okay, so these are two linear combinations of the H plus and H cross, just having the left and right helicities. You know, of course, this is very similar to what we had for the unpolarized case. It's really just this introduction of V of F. And you can see that if I force V of F to be equal to 0, then both right and left cases will have the same value of I of F. So I'm basically reproducing the top line, the unpolarized case. So this is a starting point for a polarized stochastic background. And we can now repeat everything that we have done in the last couple of lectures, calculating the omega to start with. So this was the first thing we did, omega GW of F. Remember, you start from F over rho C, the rho GW, the F. And then remember what we did, you replace rho with the expectation value of H dot contracted with itself, right? So the time derivative of the metric contracted with itself, that's what rho GW is, the energy density in gravitational waves. So you write that down first, then you do the plane wave expansion for the metric, and apply this 2-point correlation to simplify some of the integrals. What you get is pi f cubed divided by g rho c times I of f. So the energy density in gravitational waves will then really depend only on the I of f component of this 2-point correlation.
Hi, can I ask a question?
Yeah, absolutely.
So my question is, what can be like, do we know any sources which can produce these kind of polarizations?
Yeah, actually there are some. The ones that we looked at, so in my lecture notes, I added some references that you can look at these different models. But the one that we looked at first was a model of inflation, where the inflaton was an axion. So it's an axion-driven inflation. And what happens in that case, there was in that model, you assume that there is there's an interaction between the inflaton and the gauge fields that may be present. So at the end of the inflation, the axion fields kind of have a back reaction. They produce they produce the gauge fields, which then produce the axion inflaton, and that extends the inflation a little bit and boosts the production of gravitational waves at the end of the inflation, which corresponds to relatively high frequencies today. So the result of that is that this axionic field produces produces a polarized background at the end part of the inflation, which we can then search for today. There are other models, including phase transitions as well in the early universe, which we looked at more recently with Mairi Sakellariadou at in the UK and other people, but most of the backgrounds that we would be looking for would probably be unpolarized, but there are some that do predict polarized backgrounds, and you can use this to either probe them or rule them out.
I see. Thank you.
Yeah. Okay, so that was our first step. We can use this new 2-point correlation to calculate omega. Then you can repeat the same process that we did to calculate the expected value of y. And the result there is it turns out to be very similar to the isotropic unpolarized case. So I'll write down the result. So the prefactor is similar. Then we have this integral from 0 to infinity df omega prime. Bear with me, I'll define what that is. Then we have gamma I of f. Then we have q of f. And finally, f cubed. Okay, so just to remind you from yesterday, this was the expression for the expected value of y, right? So it has the energy density spectrum, it has the overlap reduction, it has the filter divided by f cubed. That's exactly what we have here, with the only difference that there is a prime, omega prime rather than omega GW. So what is omega prime? So omega prime is defined in this way. So that's equal to, okay, let me write it this way: omega GW of f divided by gamma I. I'll define all of these terms shortly. So here we have gamma I of f plus pi of f times gamma v of f. Just bear with me for a second. So gamma I of f is 5 over 8 pi times the integral over the sphere of the those response tensors, right? So f plus 1, f plus 2, plus f cross 1, f cross 2, times the phase factor, e to the 2 pi omega dotted with x divided by c. And delta x, this is a delta x here. And then gamma v is very similar to this. There is an I in here, the imaginary constant, but then the combination of f's is different. So we have f1 plus f2 cross, whoops. Sorry, I don't know what's happening here. There we go. Okay, so this would be F2 cross, and sorry, I forgot the stars. So some of these will have to be starred. Okay, complex conjugation minus F1 cross times F2 plus, and then we'll complex conjugate that one. And then we have the same phase factor. Okay, and the very last piece that's missing here is what is pi, and that's simply the ratio of V and I. So pi of F would be the ratio of V and I. So remember, the V and I are showing up in the 2-point correlation function. So these are the two functions corresponding to the unpolarized and the polarized pieces. Okay, so let's stare at this a little bit. So I already said that y looks very similar to the y for the unpolarized case. The only difference being that this omega GW is now omega GW prime. The gamma has the subscript I, and when you look at this gamma I, here it is shown, it is exactly F1 plus F2 plus F1 cross F2 cross. That's exactly what we had in the unpolarized case. So this gamma I is exactly the same overlap reduction function that we've been dealing with until now. Gamma V is a different overlap reduction function. It has to do with the cross coupling of the two polarizations and in the two detectors. So this gamma V shows up in the definition of omega prime. So omega prime, if there were no polarization, V of F would be 0, pi of f would be 0. Gamma, so this term would go away. Gamma I would cancel gamma I here, and omega prime would be exactly the same as our omega, the template spectrum that we search for. However, if there is polarization, so V is non-zero, this pi could then be a non-zero. It takes values between plus and minus 1, multiplied by this other overlap reduction function. It changes effectively the overlap reduction function for the polarized background relative to the unpolarized one. So the ratio of this new polarized overlap reduction to the original unpolarized one will not be 1 anymore. And so you can think of this omega prime as the original omega, the original energy density, distorted, if you like, or convolved by the new overlap reduction that includes the polarized term. So in the way we're doing the analysis now, the expected value of y is no longer simply the omega, the energy density in gravitational waves, but it's the energy density distorted a little bit by the presence of the polarization in the background. So what that means is that we can now do our analysis exactly as we did before. We proceed with a cross correlation of 2 detectors and so on. We calculate our y, but then in the interpretation, in the very last step, we don't interpret this y as the energy density, but as the energy density that has been modified by the polarized overlap reduction function. This analysis has been done. As I mentioned, we studied already a couple of different models. So maybe I'll switch to slides again. Let me share the slides again. Okay, so this plot here shows the gamma I and gamma V. Gamma I, remember, is the original unpolarized overlap reduction. So that's in this case for Hanford-Livingston, that's this solid black curve. You see the gamma V, which is the black dashed curve, is different, especially at low frequencies. So gamma V encodes the presence of polarization for this particular detector pair for Hanford and Livingston. Now you can also look at other. So if you add another detector, so in this case we added Kagra, and you look at the Livingston-Kagra overlap reduction. This is the gray curves. The solid gray curve corresponds to the unpolarized overlap reduction. So this would be the gamma I for the Livingston-Kagra case. So you see that that's different from both of the other curves. It actually probes lower frequencies. It has lower, the zeros are at lower frequencies as well, which is a consequence of the fact that the separation of Livingston and Kagra is much bigger than the separation of Livingston and Hanford. But also you see that gamma V is different yet, right? So it's yet another curve, and it's different from all of the 3 others. So the reason I'm showing all of this is by adding detectors and having more than just one pair, so adding multiple baselines here, you have more sensitivity to the presence of other polarization, right? So you can do this not just for the plus and the cross, or the right and the left polarizations of the standard gravitational wave polarizations, but you can do the same thing for non-GR polarizations, like the scalar modes or the vector modes and so on, which don't exist in GR. But you could do this analysis for those modes as well, and it would flow the same way, exactly the same way. It's only that the gammas will be different from the gammas that we're using here for the right and the left polarizations. So here's some results that we got. This is several years old now, looking at the Axiom polarization model that I mentioned before. And here we're Actually, for this case, we're just looking at the power law. So we're using simple power law with index alpha, and you can see we treated pi, the ratio of v and I, as a free parameter. So you can see that our limit, which I believe was the S5 limit, so this is the initial LIGO results, was constraining the positive polarization a bit more than the negative one, which is a consequence of the fact that basically of the geometry of the Hanford-Livingston detector pair. The other thing that I wanted to show is this one here. So these are simulations. If we simulate the background of certain omega alpha and of certain polarization pi, then we can try to recover both omega and pi using the same likelihood maximization that we talked about before. But now we have an additional parameter, which is the parameter pi. And you can see that if we use just Hanford and Livingston, this will give us the outermost contour. And then as we add Virgo, the contour shrinks. As we add Cagra, the contour shrinks further. And this is just the indication of the fact that different detector pairs have different sensitivities as a function of frequency to these different polarizations. So putting them together actually allows you to improve on any individual pair, and the improvement, as you see, is non-trivial. Okay, so this is probably another good spot to stop and see if there are any questions on this polarization recovery and searches for the polarized backgrounds. Everybody okay?
I had one question. So, am I right if I say that polarized background means that there is more power in the H plus with respect to the H cross? Polarized.
Yeah, or potentially the way I phrased it, that there is more power in HR, in the right polarization, than in HL, the left polarization. It's equivalent, right? You're just changing the basis in the plus and cross space.
Right, and for the CBCs, the inclination angle, if we expect it to be like uniform in cos.
Yeah.
So is that the reason why we expect it to be unpolarized, or?
Yeah, exactly. For the CBC case, for exactly that reason, we don't expect any difference between the plus and the cross, or the right and the left, because the orientation and the inclination angles are basically randomly distributed. So for when we average over the whole sky, over all the sources, we don't expect to see any difference. If we did see any difference, and we can search for it with these techniques, that could be an interesting piece of information. It will have some astrophysical implications.
I see. Okay. On the other hand, if we have some like alternative theory, then this can be used to see the, I mean, some other basis also, like tensor versus vector or tensor versus scalar.
Yes, exactly. So I kind of alluded to this. If you had other polarizations, non-GR polarizations, like the scalar or the vector and so on, you could add them, and some of the papers that we have published did that as well. You can add these additional polarizations into the mix, and then you can try to separate all of those pieces, and that allows you to put constraints on general relativity to basically test it. Another perspective here is, and I think there was a question on this related to this maybe a couple of days ago. How do you distinguish between different models, right? So we don't have different models of the stochastic background. We don't have too much to go by. We have our frequency content, we have polarization, we have directionality. So eventually, and we have not gotten there yet, but eventually we would want to be able to do a global fit of maybe some more complex model that has multiple contributions and do the effectively estimate the energy budget of the stochastic background. So maybe there will be some contributions from the CBCs, and maybe there will be some contribution from the early universe models like maybe the Axiom inflation or some phase transition models and so on. And we would want to basically figure out how much each of these is contributing to the overall stochastic background, to the energy density. So to do that, we would want to fit in frequency, we would want to fit in polarization, and we would want to fit in the direction of the sky. So having this kind of capability to identify and distinguish between polarized and unpolarized backgrounds will be needed to really figure out which model is contributing and to constrain the parameters of those models that are really contributing to the stochastic background. Hope that makes sense.
Yes, yeah, it does. So I was just wondering one more approach, which is the null stream analysis. If let's say we have we divide the data into the time scales at which the antenna pattern functions don't change, and we extract the individual polarizations, and then find the cross correlation between. Okay, then it won't be the cross correlation. It would be just the power in the individual polarizations, I guess. And
so I'm not sure I follow. Could you try one more time?
I was asking the null stream analysis where we invert the equations, like the linear equations that the data measured at each detector is a linear combination of the different polarizations, and we invert that to extract each of the individual polarizations. And from there also the from there also one could find H plus and H cross, and finally the but it won't represent the omega GW probably.
Yeah, so you're looking for the null stream in strain, right? Combining different detectors.
Right. Yeah.
Yeah. I would have to think more about that one. I mean, the information should be there, but I don't know how. Yeah, I don't know how easily extractable it would be.
Right.
Yeah, I'm not sure about that. That may be a bit more complex.
Sure. Yeah. Thank you.
Yeah. Okay, let's switch back to my scratchpad. So our next target. So we have done the isotropic and unpolarized case. Now we have seen how to deal with polarized situations. The next target we have is to look for anisotropic stochastic gravitational wave background. So the question there will be, so what we have done so far is we said that no matter what direction I look at, the stochastic background will be the same on average. But what if I have some intrinsic directionality? And at first, it might seem impossible to do this because we're dealing with only two detectors. And so the only piece of information that we have is basically the relative phase delay or time delay between two detectors, right? So if I have a gravitational wave coming from some direction on the sky, maybe it will hit Livingston first, and a little bit later it will hit Hanford. So I have some time delay, and this time delay can tell me, along with the information that the waves propagate at the speed of light, this time delay will tell me what directions on the sky could this wave could come from. But there are there's a whole a set of points, a locus of points on the sky, which would give the same time delay between Hanford and Livingston. So in principle, when you have two detectors, you cannot triangulate. You cannot figure out where on the sky the signal is coming from. The reason we can actually get away with this analysis is because we assume that the signal or the stochastic background is persistent, which means that it's always there. It's always the signal from that particular direction. The sky will always be arriving and hitting the Hanford and Livingston detectors. But the Earth rotates, so the time delay between the two detectors will change as a function of time as the Earth spins. So this rotation of the Earth then basically allows us to make independent measurements of the sky with different orientations of Hanford and Livingston as the Earth rotates around itself. And this allows us then to break the degeneracies and pinpoint the directionality of a source. So that's kind of the intuition here. We indeed have only two detectors. We cannot triangulate with them, but if you assume that the source is persistent, then you can effectively take snapshots of the sky with many detector configurations as the Earth rotates, and that allows you to break the degeneracies and figure out the directionality. Now, in mathematically, the challenge is, or the starting point, I should say, is again the same. We go back to the two-point correlation function. So we have HA star at frequency f and direction of propagation omega, and we multiply it with HA prime traveling at frequency f prime and in different direction omega prime. So A and A prime again are polarizations, and we're going to write this again. We're going to have, so there is a prefactor of 1/4 now. Then there is a delta function. So we're going to assume that the two polarizations are must be the same. We have the delta function in frequency again. We have a delta function in omega. This is a two-dimensional delta function. And then remember, when we dealt with the isotropic background and unpolarized background, we simply put H of f here. Now, in this case, we are going to have, we want to allow for directionality. So that H of f will be replaced by a different function, which I'm going to label as curly p, which will be a function of both frequency and the direction. All right, so what does this mean? So again, like before, we're going to assume that waves coming from different directions are uncorrelated. Waves at different frequencies are uncorrelated. Waves at different polarizations are uncorrelated. But if they're coming from the same direction, same frequency, and same polarization, then this P function will capture the power in that particular wave. And that power will depend on the frequency. So that's just the same as H of f that we had before. But now the power will depend on the direction as well. So that's the difference we make. This 1/4 here is completely arbitrary choice. Of course, you can absorb it inside of the curly P. It's included there just to account for a one-sided strain power. No deep meaning. So how do we then proceed? So the common way forward is to assume that this function, curly P, is separable, so that I can write curly P of f and omega as a product of two functions, one which is purely a function of frequency, and the other which is purely a function of the direction. Okay. You can ask, is this a safe assumption? There are now models of this function for the compact binaries, and those models are actually showing some correlation between f and omega, so that you couldn't really separate them cleanly like this. But at least in the LIGO band, this assumption for that particular model seems to be okay. The H of F will make similar assumptions as before. We'll assume that this is some power law, and we'll call this beta, the power index beta. This is basically the same as alpha minus 3. If you look back, typically what we assumed is that the omega is a power law, but the omega and H are related with this F cube term. So this just works. Okay, so now we have a 2-point correlation. We can again, for the third time, go through the same kind of calculations that we did before. So the first one is to calculate what is omega GW of F. So again, remember how this looks like. So this is F over rho C times the derivative of rho GW with respect to frequency. Rho GW is, again, goes as the expectation value of HAB dot contracted with itself, right? So what this amounts to is we have to expand HAB in the plane wave expansion. So you remember that from the previous lectures. Take time derivatives of those, calculate the expectation value, which will amount to using this assumption here, and then use these delta functions to solve some integrals, and eventually what you get is this. So 2 pi squared over 3h0 squared. We have the F cube term like we did before. We have H of F just like we did before, but now we also have the integral over the sphere, over the sky, of P of omega. Okay, so this is the non-curly P that shows up here. Okay, so it's very similar to before. If you had an isotropic background, this is your background. To proceed further, we need to, it turns out very convenient to expand this function P of omega in terms of some basis on of functions on the sphere. So we will write P of omega as a sum of P alpha. So these are some numbers, coefficients, times E alpha of omega. Okay, so the summation of our alpha is assumed over repeated indices. So E alpha are some functions. They could be pixels, they could be spherical harmonics, or any other basis of functions on the sphere. So what we're doing is we're just expanding or decomposing this function P of omega in terms of that basis. So for example, if we use a pixel basis, this would amount to writing P of omega as some P sub alpha prime, so some particular omega, P of omega prime, where omega prime is some particular direction of the sky, times delta of omega comma omega prime. Okay, so what does this mean? Here we're assuming that there is a single source on the sky in some particular pixel, some particular direction omega prime. Any other direction omega will have P of omega will be 0, but in that particular direction, it will have some value of P of omega prime. Okay, the alternative is spherical harmonics. Okay, so here we will write P of omega as an expansion in the spherical harmonic basis. So we'll have PLMs, these are now coefficients, PLMs, times the spherical harmonic YLM, a function of omega, where the PLMs can be evaluated using the integral of P of omega multiplied by YLM, there's actually a star here, of omega hat. So this is effectively like the Fourier transform, except instead of the exponentials with the phase factors, we're using the spherical harmonics. So any function of the sphere, including the one that we're interested in, can be written as an expansion in spherical harmonics YLMs. Okay. So with these definitions, we can now proceed to calculate the y hat estimator. Now, in the spherical harmonic, in the directional case, we do the analysis slightly differently. The notation becomes a little bit more cumbersome, so we adopt this kind of notation. So we will write C with indices of f and t to denote this particular thing. So 2 divided by t times S1 star of f times S2 of f. Okay, so this is basically the integrand of y without the filter. Okay, so it's a cross correlation. We're basically taking the Fourier transforms of the 2 detectors, S1 and S2, multiply them together and scale them. And C will be a function of frequency, but it will also be a function of t in the discrete sense, because we have divided the data into many discrete time segments. And this t now is an index that tracks which time segment we're analyzing. And in practice, f is also a discrete index because we're doing a finite Fourier transform or Fourier transform of a finite time segment. So the Fourier transform will really be a Fourier series, discrete series, and these f's will then have just a series of discrete values. So CFT is in practice is really just a series of it's a discrete quantity, and it has 2 discrete indices f and t for the frequency and time. So this instead of using y, we're using c sub ft, and our goal then will be to calculate what is the expectation value of CFT. Okay, so this will be 2 over t times the expectation value of S1 star of f and S2 of f. Which, of course, just like before, we're going to assume that the noise term and the noise strain terms will not be correlated, so they will go away, and this will amount to calculating the expectation value of H1 of f star times H2 of f, where H1 and H2 are the strain signals in the 2 detectors. So the next thing we do, as usual, is we expand both H1 and H2 in plane wave expansion. So we will have a sum of over A and A prime. We'll have the integral over d omega and d omega prime. And then we will have, for the first one, for the H1 star, we will have HA star of f and omega. And then we will have the exponential term, so e to the 2 pi I f omega dotted into x1 over c. And then we will have the f1, which is a function of omega and time as well. And then we'll have the other one, h a prime star of f prime and omega prime. We'll have the second exponential, which has minus 2 pi I f prime omega prime dotted into x2 divided by c. And here we have f2 a prime omega prime and t. Okay, let me make sure I got everything here. Yeah, it looks like I did. That should close the expectation value here. So now we impose the 2-point correlation, our assumption. So we replace the 2-point correlation with those delta functions. Oh, I should say a couple other things. So there's a factor of 2 out. Whoops, sorry about that. Okay, so there's a factor of 2 here. I've swept a little bit of the calculation under the rug having to do with the finite delta function in f minus f prime, which actually has to be evaluated because we're using the same frequency for both H1 and H2 here. We're evaluating that delta function at 0. So the delta sub t of 0 gives us a factor of t, which cancels this factor of t. So I've kind of skipped that step in the calculation. All right, so let's just proceed with our calculation here. So we have the sum and the integrals. And then we have delta functions in A prime, in omega and omega prime. And then we have h of f, we have p of omega, and then we have the same exponentials. So I guess I'll rewrite them here. Okay, and the response factors. Okay, and the delta functions now simplify everything. So we now have a single sum over A. It should be A prime here. So we have a single sum over A, which comes from the delta function in A prime. One of the omega integrals goes away because of the delta function in omega. So now we have omega, just a single integral over omega. And omega prime is forced to be equal to omega. So this will now be, we'll have h of f term, we'll have p of omega term, and the exponential will now look like 2 pi I f omega hat dotted with delta x divided by c. And then the last two terms will be evaluated at a and at omega. Okay, so no more primes. And this I can now write as so h of f can come out of the integral and the sum. So I will write it as h of f, and then inside of the integral I will write so this will be the integral over d omega. We'll have the function p omega, and everything else I'm going to lump into this function gamma, which will be the equivalent of my overlap reduction. So this will be a function of omega, f, and t. So let me write it explicitly what it is. Gamma of omega hat and f and t will be this sum. There is a factor of 1/2 out front. Sum over a of e to the 2 pi I f omega dotted with delta x over c times the response factors. Okay, so this is very similar to what we had before. Before, you may remember, we had h of f times the overlap reduction function gamma 1, 2. We have a similar situation now, except that this overlap reduction now is multiplied by p of omega. So if p of omega were isotropic, the integral of this gamma function here would be exactly the overlap reduction function we had in the isotropic case, in the gamma 1, 2. But because this p of omega could be non-trivial, this integral, we can't do it. It depends on the actual distribution of the stochastic background on the sky. So again, if that were isotropic, then this integral will be just the integral of gamma of omega ft, which will give us the usual isotropic overlap reduction function.
Vuc, in the previous expressions, you have a factor of 2, but shouldn't that be 1 by 2 itself? Because when you substitute it for or
Yeah.
expectation values of yeah, HA prime, you had another 1/4 factor, right? So that
Yeah, let's see. So there was a factor of a 1/4, which comes in when we evaluate the 2-point correlation. So that factor of 1/4 would come in when we go from this step to this step. So this 2 should have been 2 to the power -1.
right.
Okay. And then this factor shows up in the overlap reduction function. We put it in there. So I'm sorry about that, and thanks for catching it. Does that make sense?
Yeah, it does. Thanks.
Yep. Okay, well, I think that's it for today. We're out of time already, so we'll stop here. I'll answer questions if there are any, and then we'll continue tomorrow.
Thanks, Vuc. So if there are questions, please speak up or type in the chat.
I have a question about tomorrow's tutorial, but I'll wait for everyone to finish asking this question about today's lecture, and then I will ask.
Since there are no questions, you can go ahead, Aditya.
Yeah. So Vuc, in day 4's problem, you wanted people to make a simulation for a toy model, right? To compute the correlation estimator. And so in one part of the problem, you have to take some constant h over a Gaussian noise. In the other part, you have to take a Gaussian distribution over a Gaussian noise, right? So the parameters are not given. I was wondering, like in the second case, when you wanted people to take a Gaussian distribution over the Gaussian noise, you wanted them to have a finite mean, right? Not a zero mean, because a zero mean should mimic the noise itself. And if you are taking independent distributions for both the cases, they will just mimic the noise. So we could
actually. Yeah, sorry, go ahead. Didn't mean to interrupt.
So we could use some finite mean for that, right?
Actually, you don't have to. So the reason I wanted you guys to go through this is actually has to do a lot with the point you're making. So if I have two noise series, so let's so here's one time series for this would be S1 of t, and then for S2 of t, we'll have a different noise series. They're both fluctuating around 0. Okay. So when I take a product between them, so when I calculate S1 times S2, S1 of t times S2 of t, at any given time, the product could be either positive or negative, right? At one particular time, maybe it will be slightly positive. The product will be slightly positive. At another time, it may be slightly negative. And when I sum over time, this should approach 0, right? Because I'm basically adding some positive and some negative numbers, and the result will be converging towards 0. However, if you have two noise, so here's a noise time series. So this is my S1, and it's going to be very hard to draw. And here's my S2, and let's suppose that they're exactly the same. They're noise. Both of them are noisy. There's no particular waveform, but it's the same noise. So I would have to. I'm trying very hard to draw this in the same as above. Now, when you do the product of S1 of t times S2 of t, this product will be always positive. Okay, because both S1 and S2, if S1 is positive, S2 will be positive as well. When S1 is negative, S2 will be negative as well. But in both cases, the product is positive. So when you sum over t, numbers that are always positive, this will be larger than 0. So even though these are Gaussian processes, so we have mean 0, and their noise. They don't have a particular waveform. They track each other, which means that the product will be positive, and therefore, when you sum over time, you will get a number that's larger than 0. That's kind of I wanted to. Your toy model should reveal this, and that's really what we're after here. The stochastic background is a noise signal. It's a noisy noisy waveform. It's a noise. It's a random waveform, which is Gaussian, and it's centered at 0. It's positive as often as it's negative. So the stochastic background will be actually following this kind of a situation. It will be noisy in both detectors, but in the same way. If one detector is positive, the second one should be positive too.
Yeah, I understand. Thank you.
Yeah, that's a very good point to discuss and to understand.
Okay. Thanks a lot, Luke. So we meet tomorrow for the last lecture. So thank you very much.